Okay, hello everyone. Um, we are group 6. I'm Kenneth Brian Theodore, student ID 1130211130, and my teammate is Nalando Alvin 1130211132. We're gonna be presenting our project. I'm gonna be presenting on our project about uh, our text classification. Okay, so first, our motivation is because cancer continues to be one of the leading causes of death worldwide, and we want to use ML, or machine learning, to classify PubMed abstracts to support ongoing cancer research. And yeah, this can make faster literature retrieval and also better support for researchers and clinicians. This project, we aim to classify from the top 10 cancer found in men, which is right over here in the middle. And we take the data from this ranking data is from the World Cancer Research Fund website. Okay, so next we're gonna be explaining about the data collection. Okay, so how we collect the data is have we, as we've mentioned before, is we take a look at the rankings, the top 10 most prevalent cancer found in men from the World Cancer Research Fund, and then we access PubMed, and we can see here, for example, we search the keyword prostate cancer, and then we save the results. First we select all results, and the format should be in PubMed, and then we parse and then convert the data into XLSX files so we can run it through the program. Okay, so after that is the data processing. Here we process the data into 5 sample sizes. The first one is 100, 200, and then 1000, 2000, and lastly is all of them. And next is we use text pre-processing to reduce the noise and improve model focus. So basically, all the lowercasing, we remove that stop word. We lowercase the words. We remove stop words, contraction, expansion, and then lemmatization, and also we remove the special characters and punctuations. This can help us ensure a clean and consistent output for classification. Next is the tests that we did in this project. We use the classifiers naive Bayes, logistic regression, linear SVM, SVC, and then linear SVM SGD. And then lastly is random forest, although we didn't use random forest later on in the project, only on the first part, because we felt that it wasn't needed and there were already linear models like logistic regression, which does the same thing and is much more effective and efficient. Also, the test results weren't too satisfactory, so yeah, we didn't use that later on. Only on the first part, which is the TF one. And these are the classifications, which is TF, TFIDF, and TIFIDF, which is hyperparameter tuned. And for the feature weighing and model comparisons, we compare the accuracy between models across all of the classifications, which is TF, TIDF, and TIDF, which that is hyperparameter tuned. And others is like determining whether classification accuracy increases when dataset increases, and also determining which pair of cancer types are most misclassified. For the first one of feature weighing, this is the accuracy comparison that we got from each model. There was minimal impact for more sophisticated models like logistic regression, linear SVM, and SGD, but there were moderate impact for naive Bayes when we changed the classification from TF to TFIDF. And lastly, the hyperparameter tuning also provided more benefits for simpler models like Naive Bayes. And from this, the conclusion we can draw is the best classifier is linear SVM and linear SVM SGD for large-scale applications. However, like overall, linear SVM with TF-IDF and hyperparameter tuning is the best classifier to use. So next is the relationship between classification accuracy and data size increase. Does the accuracy actually improve when the data size improve? And that's what we'll be looking at here. So this is the data that we got from the different data sizes. You can see there's consistently a high performance in accuracy and F1 scores across all data sizes, and we don't see any clear data size benefit as increasing data did not consistently improve performance. In fact, it peaked at 200 sample sizes with the best results across all, like accuracy and highest F1 score. But as it went to all data sizes, like the full data set, it actually showed lower scores, and this is likely due to increased complexity and class imbalance. We'll be comparing the classifiers used in this project, and we have to note that this comparison is done on the 100 subset data size. So the table on the left here is the comparison of the accuracy, and the table on the right is the comparison for the training time of each classifier. From the accuracy, we can see that linear SVM from the bolded one there is, and its SGD variant consistently matches or outperforms others, especially after hyperparameter tuning, which is when they reached the highest scores, which is almost close to perfect, score of 0.99. And for the training time, Naive Bayes can be seen as the fastest one, but standard linear SVM also provides a good balance. It can deliver high accuracy while still maintaining competitive training times, and also often sometimes faster than logistic regressions and SGD. So from this classifier comparison, our group prefers the linear SVM classifier the most. This is because it is able to provide the best balance between high predictive performance and computational efficiency. It can tie for the highest accuracy and F1 scores of 0.99 on the tuned dataset. Even on simpler feature sets like TF-IDF, it still performs at a very high accuracy and F1 scores. It is also efficient since it's consistently takes a fast time to train, and on the TF and TF-IDF sets, it trains even faster than logistic regression, and often sometimes faster than SGD as well, and it still achieves equal or better accuracy. However, the other models has their own perks as well. Like for example, you can choose Naive Bayes if you have extreme constraints on training time, computing power, and you can accept a lower accuracy. And you can also choose logistic regression if you need a slightly better model in interpretability, and because the coefficients can be examined for feature importance and performance is similar. And you can also choose linear SVM SGD if you are scaling to a massively large data set where the standard SVM becomes too memory intensive. And lastly is the misclassifications of the pairs of cancer type that happen throughout the process of the whole project. From the results, we found that the pair of esophageal and stomach cancer had uh, one of the most misclassified results. Around 4 until 9 samples was swapped across models. And also second is lung is often misclassified as esophageal cancer. There were around 4 until 8 lung samples mislabeled as esophageal, and the third one is non-Hodgkin lymphoma and leukemia, which has like 2 until 7 cross errors across each model, across the models. And lastly is the kidney, which is often mislabeled as bladder cancer. There were consistently 5 kidney cancer samples mislabeled as bladder cancer. Now, for the reasoning as to why this happens is, of course, uh, there is the biological reasoning, but we won't be getting into that. From the analysis of the behavior of all models, they all behave similarly, and confusions are found to be data driven, not model specific. And linear models like SVM, LR, and MNB rely on word co-occurrence, and they cannot distinguish context, so this may cause some classification. But we can also see the type of cancer that can also affect the amount of misclassification, because there were no models confusing prostate or colorectal cancer significantly. This could be caused because they have distinct vocabularies, so that could factor in where model can misclassify when the cancer types have similar vocabularies. Okay, here are some of the code improvements that we did. First of all, we changed the grid search CV to randomized search CV for more computational efficiency while also maintaining statistical validity. And the second one is we controlled the feature limitation. We reduced the feature from over 100,000 to 3,000 to 8,000, which is around a 95% dimensionality reduction, but it can still retain high predictive power. And next, we preserve the n-gram strategy. We use both unigrams, 1 grams, and bigrams for richer text representation. And for the key unigrams, we use informative singles terms like metastasis, biopsy, oncology, tumor, adenocarcinoma. And for the key bigrams, we use also clinically meaningful phrases like lung cancer, prostate tumor, breast carcinoma, colorectal or adenoma, and this captures the essential medical semantics and context, boosting the cancer classification accuracy. We also changed from the standard 5-fold to a stratified 3-fold cross-validation. This ensures that all 10 cancer types are proportionally represented in every fold, especially critical for rare cancer categories. This slightly reduces statistical robustness for greater computational efficiency, but it doesn't compromise class balance. And the next one is we use randomized search with only 6 combination. The original code was testing 10 parameter combinations with a 2 times 5 grid for multinomial naive Bayes, but now we use only 6 combinations. This reduces the computational cost while also still covering key parameter ranges effectively. And lastly is we replace the sequential execution with njobs -1 to enable full CPU parallelization. And this speeds up hyperparameter search and model training significantly. This is also implemented across other classifiers, so it's not only on multinomial naive Bayes here. And this is our group discussions that were done throughout the process of this project. And this is our reflection. So Alvin thought that through this PubMed article classification project, he gained a practical experience in implementing multiple text classification algorithms with TF-IDF feature engineering, and he learned firsthand how different models respond to feature weighting and hyperparameter tuning. He also learned from this project via SGD that computational efficiency can be achieved without sacrificing accuracy for classification tasks like this. He also thought that finding the improvement that our group want to make to the existing code was the challenging part. As for me, this project was very challenging mainly because it takes a lot of time to think of the improvements as well, and like with the improvements we want to make and how to finish the project in time before the deadline. And I definitely learned a lot, mainly of course about the application of classifiers and hyperparameter tuning in the world of ML, especially since I'm not really well versed in coding. So this project was very hard for me, and I needed to study a lot on the usage of ML and how to implement it. Okay. And thank you for listening to our presentation of what we did on our project. Thank you.